Okay, we'll get started. So this lecture has been pushed to GitHub, and so you can get it by running just a couple Git commands. Again, you'll change your directory into 2022 winter stats 21, and then you can do git fetch stream. And that should fetch all of the new material. So if I list everything right now, I only have through lecture 1.3, but after I fetch upstream, I will do git merge upstream / master. Oh, I'm sorry, not master, / main. And that should show that we've added a bunch of stuff. And now lectures 2-1 should show up. Okay, so again, git, once you're inside there, you're going to do two commands: git fetch upstream, git merge upstream main, and that should do it. Okay, and so all of these lectures should be here. And I know the GitHub stuff and the Git stuff is all new to everybody, but hopefully it will start feeling a little bit more and more okay each time as we do this. And then I think you'll then begin to appreciate how simple it is to kind of download new content. Because every time I push stuff, because on Canvas or it used to be CCLE, you'd have to download files individually and things like that. And for the homework, you still kind of have to do that. But as far as the lecture materials, you can just kind of do a git fetch and a git merge, and where you'll be all set. Okay. Oh, and I do want to say one thing to avoid what's known as a merge conflict. Some of you might want to edit these files as we go along. One thing I would recommend is that you make a copy, you duplicate it, okay? You duplicate it, and you call it something like, with personal edits or something, and then you edit the duplicate. And that way you'll avoid merge conflicts. Because if you make changes to the document and I also make changes to the document and we commit both of those changes, then you're, it would be like, did you guys watch Back to the Future? Where we went back to the same point in time, but then we created two separate timelines, right? Like you edited the document one way and I edited the document the other way. And so now there's a conflict. And so to resolve it, you have to do what's called a merge conflict. And that's, it can get complicated, especially with Jupyter notebooks. With text documents, it's a lot easier. So things like Python scripts and R scripts and things like that, it's a lot easier to resolve a merge conflict. But when you have a merge conflict with the Jupyter notebook, it like breaks the notebook and it becomes a huge headache. So to avoid merge conflicts on Jupyter notebooks, I recommend just creating an entirely separate document, which allows you to kind of just work on your own timeline without any kind of conflicts there. All right, but let's go ahead and take a look at what we are covering today, and we'll get into the Jupyter. That's the wrong thing. We're trying to get into basic data types on for Python. And you know what? I think what I'm gonna do. I know your first homework assignment. I'm gonna extend. I'll grant 2 extra days for it. So I'm gonna make homework 1. I'm gonna push the deadline to Friday. Okay, so it'll give you a couple extra days to get homework 1 in. And just because I know things, this quarter's been off to a little bit of a tough start here. So I hope that's helpful. and then again, you know, still have issues, just message me. We'll figure something out. But I'm going to go ahead and extend homework one's deadline to Friday, January 14th. Okay, let's go ahead and take a look. Basic data types and variables for in Python. So, you know, prereq for this class is stats 20. So you are familiar with a lot of these kind of the idea of data types in R, and the concept is very similar in Python. We just, everything's got slightly different names, okay? So you have kind of your base kind of data types, all right? So such as strings, integers, floats, booleans. So strings are your character data. For text data, integers I think are self-explanatory. Floats are numbers with decimal points, and then your booleans are true, false. And then you have the none type, which is Python's equivalent of the null value. So in R you had null, in Python we have none. And it's to indicate things that do not exist. All right, other very important data structures that exist in Python are the lists, okay, lists, and you also have its immutable sibling, the tuple, okay. We also have dictionaries, sets, and bytes, but really the most important ones in this listing are the lists, dictionaries. I'd say tuples are pretty important too. Lists, tuples, and dictionaries. And then later on, we will load libraries, Numpy and pandas, which introduce arrays and data frames to Python. But the arrays and data frames are not part of base Python. So, so we have to call libraries into this. So Python is very extensible, and pretty much as you start doing data science, you're going to realize that these are certain libraries that you need to kind of load every single time. Whereas in R, you can get pretty far in kind of stats analysis with just base R. I like using the tidyverse, and I kind of call it every time I start it up. But with Python, it's very difficult to do any data science without calling in at least pandas and NumPy. So, but anyway, let's just go ahead and take a look. So you're kind of the function that we use to figure out what type of object we have is just the function type, right? So you put in type, and here I have quotes too. So because it's in quotes, Python recognizes that this is a string, all right? And it comes back and it says str for string, right? Whereas if you put in the number 2, it's an integer. If you put in a 2.0, then it becomes a float, right? This is this is a distinction between the way Python and R handles numbers. With Python, every time you have a float, it's very distinct. It will always output a decimal to kind of, because it expects, well, to distinguish between integers and floats. True, the keyword true is spelled capital T, lowercase R-U-E. This takes a tiny bit of getting used to, especially when you're switching between languages. I'm teaching at the same time. Immediately after this class, I teach a Stats 102A, which is a class on R, and it always takes my brain like a while of making mistakes to switch between the way I spell true here and the way I spell true in R and things like that. And then you got the 0 index versus the 1 index, and you know, there's just enough things to kind of confuse you a little bit, right? Just like if you speak bilingual and you're speaking languages, sometimes your speech gets a little bit garbled. Okay, and then the none type is its own type. Okay, and none is this again this exact spelling, capital N, lowercase o-n-e. So with these things, you can start doing math. I think this is all just your very basic math operations. These are the math operations that come in base Python. If you want to do anything more interesting, you actually have to import the math library. So functions like your trig functions like sine and cosine, they are not part of base Python. If you ask, hey, what's the sine of 90, or the sine of pi halves or something, it will not work. But these base functions do. So you have the absolute value, you have exponentiation, which is star, plus, multiply, minus, divide, floor division, and then modulo, which will give you the remainder after you do floor division. So if you add two integers together, okay, x plus y gives you z, will be 15, and z is going to be an integer. Okay, no problem there. If you multiply two integers together, so x is 10, y is 5, both of these things are integers. X times y gives us 50. It's going to still remain an integer. Okay. Whereas division will always result in a float, even if the result is an integer. So if you do x is integer 10, y is integer 5, and you do x divided by y, 10 divided by 5 is 2, but it's going to be a float. And so when you print out z, it's going to show up as 2 or 2.0. It will always include a decimal to indicate that it is a float type, floating point number, and not just an integer. Let me go ahead and give you your very first view quiz answer for week 2 on Monday, and I hope I published the quiz correctly and it's available. Week 2 Monday's first view quiz answer is B as in bear. B as in bear. Okay. So when you start mixing these things, so now x is 10.0, it's a float. Y is 5, it's an integer. Okay, so if you add or multiply things with a float, integers and floats together, the result's always going to be a float. Okay, because you think of a float being a less restrictive type than an integer, because floats include pretty much all integers, but also allow for right. So I mean, you think of this integers as a subset of the real number line, and similarly, floats or integers are kind of a more restrictive type than the floats, even though mathematically, floats are not the real number line. Just make it very clear, floats are not the real number line, right? So when you do x plus y, you get 15.0, indicating that it has changed type to float. X times y, you get 50.0. And again, the 0.0 indicates that you are dealing with a float. So that's one nice thing about Python, is that just by looking at the output, when you print it out, it's always going to show you, you'll be able to tell whether it's an integer or a float immediately, whereas it's ambiguous in R. So most computer systems, when you use a floating, have a floating point number, uses 64 bits to represent decimal values. And if you've taken 102A, you understand what that means. And if you have not yet taken 102A, which is a good number of you as well, basically, one thing to having 64-bit representation, it basically means you cannot have infinite decimal places with your numbers. So if you think about the real number line and you say, well, how many numbers are there between 0 and 1? There's infinitely many values between 0 and 1. How many numbers are between 0 and 1/2? Infinitely many numbers between 0 and 1/2. And that's because you can have infinitely many decimal places. But with a computer, we don't have infinite storage. And so you cannot have a number with infinitely many decimal places. And so with 64 bits, you get about 16 decimal places, 16, 17, 16 decimal places. And basically, if you need a number with more decimal places than that, you need to use more memory to store that number. And so a floating point number, yeah, approximately 16 places of precision. And there are limitations to kind of the biggest number that you can store and the smallest number that you can store inside your computer. Okay. So here I have 2 raised to the 1023, and it gives me this big number. And if I do 2 to the 1023 plus 2 to the 1022 plus 2 to the 1021, I get something a little bit closer to the maximum value. Okay, this is basically 2 to the 1024 minus 2 to the 970 something. Okay, something just a tiny bit lower than that. Okay, if you try to input 2 to the 1024, this causes an overflow error. Okay, meaning that you have run out of space. Okay, and so it's kind of just like when you have your, where did my little calculator go? When you have a calculator, an old school calculator, the biggest number, you have 8 digits there, right? The biggest number you can store is 99999999999. Okay, and that's the biggest number. And if you try to go any bigger than that, you get an error. And that's basically what we're encountering here. 2 to the 1024 runs into an error. Okay, so one side effect about real numbers is that I'm sorry, not real numbers. One side effect is that floating point numbers and real numbers don't work in the exact same way. All right. So here, if I say A is equal to 1 plus 2 divided by 10, what is the value of A? Well, we go, oh, okay, A is 0.3. All right. And what is B? Here I got B is 1/10 plus 2/10. Okay, and we go, okay, so A is 0.3, B is 0.3. But then if I say, is A equal to B, all right, so I do a test of equality, is A equal to B? We expect these things to be equal, but they're not. And the distinction is that when this number gets stored into the computer, right? So this is you can format your numbers. So when you do print a value, like print A or something, you can specify. And this basically means I want a floating point number, but show me 20 decimal places of precision. Okay, and it says, all right, internally, this number 1 plus 2 in parentheses divided by 10, 0.3 internally is stored as 2.99999998890. Whereas B, when you do 1/10 plus 2/10, this gives me 0.30000000441. Okay, both of these things are approximately equal to 0.3, and that's close enough for most intents and purposes. But as far as the computer goes, it doesn't know that these two things, in the real number line, these two things would be equal. But here we're getting something a little bit different. It just sees these things. These are different numbers. And so when it asks, are these equal? The answer is going to be no, they're not equal. Okay. There's a function you can use called isClose. And that's going to just say, hey, these two things, yes, they are close. But that's fine. All right, so meanwhile, we have integers in Python. And one thing about integers in Python is they don't have a fixed amount of memory. And therefore, you can store very, 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 very big numbers in as integers in Python. And so if I did 2 to the 1023, the computer will actually do this, and it calculates every single position here. right? And whereas 2 to the 1024 caused an overflow error as a floating point number, you can actually do this computation, all right, as an integer, with an integer in Python. In R, integers, I think, use 32 bits of space, and so you can't do stuff like this. I think the biggest number is, I don't remember how big it is, but or I don't know, maybe not even 32 bits, maybe only 8 bits. I don't remember, something. Okay, there's only a certain number of values you can store. Okay, and so you can actually do this. You can even keep going 2 to the 1025, and the numbers just keep getting bigger and bigger and bigger. All right, so you're only limited by some kind of memory limitations, which generally, unless you try something, you know, really absurd, you probably won't hit, you know, in practical aspects, you won't hit that limit with an integer, but you might slow your computer down. This, so we've got that. Okay, exponentiation, I think we're using to do this is 9 squared is 81. There's no such thing as a square root function in base Python. I mean, there's a square root function obviously in the math library, but if you want to take the square root, you can't call square root, but you can do raised to the 1/2 power. So you can do square root 9 gives you an error. It says, so name error basically means the function's not defined, but you can do 9 raised to the 1/2 power, and it'll do it. Okay. Okay. So in base Python, you don't have things like pi. There's no e function. So both of these things give us name errors. If you want to do a little bit of basic math, okay, again, no trig functions, no sine functions. If you want to do a little bit of basic math, you have to import math. Okay, so so you can do import math. Later on, I'm going to introduce Numpy or Numpy. I don't know how we pronounce this thing. Okay, I've heard it pronounced. It's like the GIF and GIF debate, and there's probably something with a little bit more Numpy or Numpy. Anyway, I say Numpy. I think I also say GIF, but I know everybody hates that, so it's okay. That's a secret. We can use square roots now, all right? And so to indicate that you want the square root function and that the square root function is part of the math library, we use this notation. We do math dot square root. Math dot square root 9 gives us 3.0. No surprise there. And then pi, which is part of the math library, we got math dot pi. And now we have the constant 3.14. All right. And same thing with the e function. And we can say e to the 2nd power is this. Any questions? How do we feel about all of this? So far, so good. Okay, great. Thank you for that thumbs up. Let me go ahead and give you your second view quiz answer. Second view quiz answer today is A as in apple. Somebody said I should use animal names for all of these things. I don't know. What's a animal? An aardvark? An anteater? Okay. A as in some animal that begins with A.
Sorry, Professor, is math.exp1, would that just be E?
Yes, yeah.
Okay.
Math.exp1 would be E. So yeah, let's come over here and so again, if I try to do exp1 right now, I get a name error, but I can do import math. Math.exp1, and this will be the E value. And I think I can just do math.e as well, and that will give us the thing. Yes, so do you have to import the math library for each session? You have to import it every single session, yes. Every session you want to use it, okay? You have to import it every session. So basically, every time you start a new notebook, okay, something like this, all right? Again, if I tried to do exp1, it gives me an error. So if I want to use it, I have to import math. Okay. Just kind of you think of this every time you start a new notebook. You think of this as my train of thought. Oh, you think of it as like restarting restarting the computer or something, and you just have to kind of load it up every single time. Okay, right? You restart your computer and you want to use Excel, you gotta open up Excel. You want to use your browser, you got to open it up every single time. But is there a way to show more decimal places? So by default, I think it shows, how many does it show? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 decimal places. And this way will kind of be correct each time. And I think that's good. I think the default settings are pretty good. You can always do print, and you can put in there's like some format languages here, and let me kind of, I forget, and there's ways to format your strings when you print them. Where did I go? So this is one way to print more decimal places, and you can look up Python format strings as far as how to get certain things. And so math.e, we know if internally they store more decimal places versus yeah, so they do store a few more decimal places here, but I think, what is the actual value? Okay, so how accurate is this? So this is the true value of E, and internally with our floating point precision, I can get up to 845904. 845904.5. Okay, we can get up to that. So we are able to store up to that level of precision. Okay. Oh no, 045. Oh, I'm sorry. So it is correct up to here. This is the default printing, and beyond that it is incorrect. Okay, so after 045, 23536. Okay, beyond that, we are not able to represent it correctly with our limitations of the floating point number, right? So if you think about the real number line, the location of E is here, but with floating point numbers, we can't represent all infinitely many values. And so there's kind of like discrete locations of things that we can represent. And the closest one is this, which is only accurate up to the 045 portion, which is the default printing value. And if you want something more precise than that, it's basically lies. It's lies after that, okay? And it's just, you know, it would be kind of like someone asking, how tall are you? And you might say, oh, I'm 5'9", okay? And someone else might say, I'm 5'9.5", okay? But then if somebody says I'm 5'9.11788865" inches tall, it's probably a lie, okay? maybe they took their height in centimeters and then they did a conversion into inches, and so you get all of these decimal places and stuff. But that's not the truth, right? And you learned about kind of this, I don't know if you took chemistry and you had like significant digits, and you had to learn that like when you took a measurement and there was only so many significant digits here, and you do multiplication conversions and stuff, you can't just pretend that all of these decimal places of precision continue. And similarly, there's, you know, rules like that. I don't sweat it too much, okay? And I'm not a stickler about these things, but it is important to note that when you store numbers in the computer, it's not real numbers. You don't have the same properties of the real number line. Okay, so you got the sine function. The sine function in pretty much most computers by default will be using radians. So here we've got sine of pi halves, and that gives us 1.0, and we're happy about that. Okay. Boolean types, you got trues and falses. So capital T, lowercase RUE is the keyword for true. That's the only accepted spelling. And capital F, lowercase ALSE will be false. Yeah, math also has math.cosine and math.tangent. Yeah, so you can look up Python library. Click and so, oh, all right. So one thing, when you use a search engine and you type in something like Python math library or something like that, the best resource is going to be the ones that come from the python.org. Okay. Now, Stack Exchange is a great resource, and there's a bunch of different blogs and stuff that, you know, people write their things. But truly, the official documentation is always going to kind of be your best resource. And so the official Python documentation is very good. There's a bunch of libraries, and this is one thing you'll discover, and this is you'll come to appreciate good documentation. And so thankfully, the official Python libraries have very good documentation. You'll see a lot of other libraries that people have created that are poorly documented, and you realize what a joy it is to have good documentation. So anyway, the math library, it's got a listing of all of the different kind of functions you can have. So you have the arc cosine, arc tangent, and then you have the hyperbolic tangent functions, which I still never fully understood. I think this was, we had that week in calculus or whatever, but I only just remember like the suspension bridge and trying to remember, but I don't remember. Okay. So, you tried using a different spelling of true, and it says you can't do that. You can't do that. That's not defined. All right, strings. Strings are anything with quotes, right? You put in quotes, double quotes, or single quotes. Now you got a string. Okay. We will cover strings at a deeper level, but just for now, let me give you some of the most very basic of string functions. Number one, the length function. The len tells you how many characters are in a string. Characters include spaces. So 1, 2, 3, 4, 5 for hello, exclamation point counts, space counts. So we're at 7, 8, 9, 10 for how, 11, 12, 13, 14, 15, 16, 17, 18, 19 characters. Okay. And so that's how many characters we have there. You do, hello, how are you? And then 4 times message 2 gives us fine. Okay. So this is your multiplication with strings, which Python lets us do. We can do multiplication and we can do addition with strings. And so in a pinch, it's not the best recommended method, but if you want to keep like making a longer string using variables and stuff, you can use the plus sign and Python will do it. It's I don't know if it's the best way. It requires a lot of overhead to do that. All right, assignment. We use the equal sign to assign values, right? You always have to put the variable name on the left, and you always put the actual value on the right, okay? And it's gonna always do the stuff on the right gets assigned to the name on the left, okay? Not the other way around. So if you have, you can so if you put in like two variable names or something, it's always going to be the one on the right gets assigned to the one on the left. Okay. When you do assignment, Python's not going to print anything out to the screen that says like, oh, okay, n is now gets the value 5 or something. But later you can ask, hey, what is the value of n? And it says it's 5. Okay. This is exactly doing what we expect it to do. One thing is that this gets a little bit more CSy than I care to get. All right. And so students sometimes ask about, what's the difference between CS and coding? And it's a huge difference, right? So CS is really kind of like this theory of what is a machine capable of doing, and what, how do we think about all of this stuff? Whereas coding is just kind of like, oh, let's build something, right? It's like the difference between architecture and like building a box. Okay. We wouldn't say the two things are exactly the same. So we're more on the just building stuff, coding side here. Okay. So anyway, just to contrast Python to some of the other languages like C or Java. Okay. When you define a variable, you are defining basically a container. You're defining something where it stores values. Okay, so you define like the integer x, you define an x container, and we say this container is going to be an integer type, and it's only allowed to contain integers. And so right now we're going to put the integer 4 into here, and this would be how we would write something in C or C++ or something like that, and we put the value 4 in there. Okay. Whereas in Python, when we write something like x equals 4, we're defining the variable name, which in this case is technically a pointer, and the pointer's name is x, and it points to this value 4. Okay, it points to, in memory, there's a bucket with the value 4, and we are just saying x points to this thing. Okay, we're not actually declaring a variable. We're not defining an x bucket. Okay, 4 is a value that exists, and we're going to have x point to that. And so we can create new values, and we can just change the value type on the fly here. Okay, so now I'm going to say, all right, let's just change x, and it's going to point to a new value, 1. Okay, x is now going to point to a new value that's a string that says hello. X is now going to point to a list that contains 1, 2, 3. All we're doing is we're just reassigning where that variable name x is pointing to, rather than changing the value that actually is going into the bucket. Okay, again, we don't have to worry too much about it, because Python kind of does all of this for us. I don't know if you ever took like a C class or something, you had to like when you got rid of a variable, you had to like remove it from memory, otherwise it keeps that thing. And Python in the background has something called the garbage collector, and so when like nothing is pointing to something anymore, the garbage collector goes, sorry, we don't need you anymore, and we're going to clear up the memory space. Okay, so anyway, this allows Python to be this dynamically typed language, meaning like we can switch. X can now be an integer, and then in the next moment it can be a string. It can become a floating point number, and it doesn't mind. It doesn't care. Okay. When you name variable names, this is like one of the hardest things. This is like an old joke in computer science. Is like there are 2 things in computer science that are hard, and I don't remember one of them. What it was like something, and then the other one was like variable names. Coming up with good variable names. So there's a few rules, right? I think they're all pretty straightforward, right? It can't start with a number. It can contain numbers, but it can't start with a number. And then the only symbols that are allowed is the underscore. All right, you can't put spaces in a thing. And I know like when you create folders on your computer, you put spaces in there, and it always like it's always a little jarring for me. I always use underscores, just and I think you're noticing now that you're like using the command line and you have to escape your spaces with a backspace. You're like, oh yeah, this is why this is why people don't like to use spaces in their folder names. But you have underscores. Okay, these are the keywords. Things like false and true and none. You cannot create a variable name using a Python keyword. And these are the other keywords. These are all reserved words that serve a very important function in Python. So you cannot create a variable named if and is or something like that. And these are other things, right? So one thing is lambda. Lambda contains a very, has a very special function in there. And this is the only one that looks like a possible variable name. That everything else, I think we would say, yeah, that makes sense that you shouldn't call it that. Okay, but we have that. Okay, Python keywords. All right, let me go ahead and give you your last view quiz answer for today, which is B as in bear, B as in baboon. What's another animal that starts with B? Badger. Badger, like Hufflepuff, right? They're the badgers, right? Okay, anyway. All right, I got assigned to Hufflepuff, so it makes sense. It makes sense. But anyway, all right. The art of naming variables. What do we do? Okay, we want to think of good variable names. All right, and it's actually hard to think of good variable names. You know, it's always easy to just say, all right, we're gonna have variable X and variable Y and variable Z. But honestly, those are probably like the worst variable names you can pick because you have no idea what it's referring to, right? If you say X has this value, it could be anything and there's no context, right? Ideally, your variable names provide a little bit of context and you understand what it is, right? So the goal is being able to read your program, understanding what the variable is without having to kind of go back to the assignment statement to remember what it was all about, right? So later on, you don't want to be like, oh, what is this value X again? And you have to go back to assignment and you go, oh yeah, this is when I was assigning like height measurements and stuff, right? If it's height measurements, call it height, right? So clear and concise, preferably English, right? And don't use special characters, right? So you can, I think technically you can use special characters, which, you know, you put these little double dots and stuff in general, just so you don't break people's code, especially, you know, some older system, just stick to the ASCII keys, right? Which is basically, if you have a US keyboard, it's going to be just all the letters that you can type on your US keyboard without having to go into your special symbols menu will be your ASCII keys. All right, so these are not good names, right? You just have S. This has no context. It's like X, Y, or Z. We have no idea. SID maybe is a little bit better. We go, okay, there's some kind of identification number, but it's also, you know, not that great because it also looks like SID. We're like, what is that? Okay, so we don't know what they, right? This is also a very bad name because it's way too long. It says Finnish Meteorological Institute Observation Station Identification Number. Okay, it's a little bit more descriptive, perhaps not very useful because who wants to retype that? Okay, thankfully we have tab completion, right? That's such a lifesaver. Is that if we recognize that variables exist, we can often use tab completion to get it. Okay, so we can do a couple things, right? So there's snake case, which uses underscores between words. Sometimes snake case is called pothole case because of the underscores do, you got little potholes here. You have a lower camel case and upper camel case. Basically, you don't use underscores, but you indicate new words with capital letters. And the only difference between lower camel and upper camel is that the very first letter is lowercase for lower camel case, and the very first letter is capital for the upper camel case. So you have FMI station ID. That's probably a little bit better. FMI station ID also. This would be the camel case, and this would be your snake case. Other naming considerations. So these are suggestions. These aren't laws. And I'm not a huge stickler. So I guess these are tips, but then you do what you want, right? but they're good habits to form. They're good habits to form. So if you're going to create a list, that the name of the list should be plural to indicate that it contains multiple things in there. Okay. And if the list contains names, it's useful. So for example, if you call it fruit and it's a list of fruit names, this is not great. Okay. It's good. You know, at least there's context. At least you didn't just call this F. Okay. At least there's some context here. So you get a bonus for that. Let's see. This is a little bit better, right? We got fruit and fruits. Fruits now indicates that we're going to have multiple things here. And then better would be saying like fruit names, right? We got the names of fruits. And, you know, if you have another list which contains values or something, you can call it fruit prices or fruit fruit quantities or something. And that will provide a little bit more context. Okay. One thing you kind of want to avoid is just continuing to add numbers. So you'll have like fruits 2, fruits 3, fruits 4, something. Unless it's very much like this sequential thing where it makes sense to have the numbers. You know, it's just kind of like your naming file conventions, right? When you're writing an essay, you have like draft 1 and final draft, final draft, final draft. This is the one we're turning in. Okay. If the thing you're gonna do stores a Boolean, you kind of want to turn it into like a yes/no question, right? So these aren't great variable names, selected, right, or fruit. You can say is selected true, can write true, has fruit true. These kind of make sense, right? Because the question is the answer to a question yes or no. Is it selected? Yes or no? Can it write? Yes or no? Does the thing contain fruit or has fruit? Yes or no? Versus this just the inclusion of like a little action verb into the variable name provides it more context. And also, when you see a variable name like this will clue you in just from reading the variable name that it should clue you in that this is going to be a Boolean value containing a true, false, or yes, no type answer in there. Okay. Adding just a simple descriptor word, right? So you have rows. It is a good variable. I mean, it's a variable name that can be useful, but again, depending on how you are defining how it's being used, right? If you're trying to define some kind of data frame or something, some kind of function, it's often better to have just a little bit of description here, right? So you can have current row, total rows, the maximum number of rows, minimum number of rows, and these descriptors just add a lot more context and make your variable names richer and more useful as you're working. Again, the whole point of coding is you want to make your own life easier, because the person who's going to be reading your code the most is going to be you in the future. And if you follow good practices today, you in the future will be thankful for what you've done today. Versus, because if you've ever tried to read somebody else's code, oh my gosh, it's such a nightmare, right? Because you're like, what were you thinking? Okay. And if you ever write bad code, you go through the same thing and you go, oh man, what was this person thinking? Oh, but guess what? It was you. And it was you, 3 months ago. And you can't ask that person questions. All right, function names, do some kind of, if the function is going to modify something, use an action verb. And if it doesn't modify it, but returns kind of a modified version of the object, but doesn't actually modify the object itself, use a passive form of the verb. So a function that will take a list and modify it by sorting it, we can call it sort. Okay. On the other hand, you can have another function that doesn't actually modify the list itself, but returns a copy of it that ends up being sorted. We would call that sorted, all right? And I know I'm over my time here, but Python, base Python has good kind of follows this good practice, right? So here I've created a list called car brand names, and I can do car brand names.sort, and it actually sorts the list, right? Over here, I've got car brand names, a new list. And if I do sorted car brand names, it returns a copy of it that's sorted, but it leaves the original list in its original order. Okay, so there's just it's a subtle difference. One is actually sorting the list and modifying the list itself, and another one is returning a copy that is sorted. And there's a and I hope that kind of difference makes sense as far as why there are basically two sort functions, but they actually do different things and they are named accordingly. Okay, anyway, I think that's pretty much it. This is if you try to do some of this stuff and it returns errors and stuff, but that's all it for today. Have a good rest of your day. I will extend the homework deadline for homework 1 up to Friday. And other than that, I will see you guys on Wednesday.
Thank you, Professor.
Thank you, Professor.